Good morning, everyone. Uh, in the previous lecture, we have been through. We learned this statement of division algorithm, and then we classified we classified all the subgroups of Z of this group Z. Earlier, we have seen that the subsets of Z of the form Kz, that is the subsets of Z consisting of multiples of a given integer k, the integral multiples of a given integer k. So such a subset forms a subgroup of Z. Okay, and then the aim of this theorem was to indicate that these are precisely all the subgroups of Z. Okay, as k varies over various integers. Yeah, and I think during all that I have also, so these handwritten comments are missing here. I think I have also asked you while lecturing, I asked you to see what happens. Is there a relationship between, oops, not really right. Is there a relationship between kz and minus kz? Okay, the multiples of integral multiples of minus k, the integral multiples of the set of integral multiples of minus k and the set of integral multiples of the integer k. Is there a relation between them? Okay. Anyway, so there are certain interesting questions to think about. Interesting and too easy questions to think about. But this might be easy, but this is necessary to think about such questions, even if they're way too easy. Okay. So now this is a good time to get into the next notion, which is quite important, and it appears. It appears in various places, sometimes in disguise. Okay. Yeah, so it's good to have a formal understanding of that notion. So it's called equivalence relations. Okay, so as you may imagine that the relations will be the fun. More general than this. So indeed that is so. So you'll first learn the notion of relation. Okay, and then mm, just give me a moment. Then in a while we'll learn the notion of an equivalence relation. Okay, yeah, so it's here. So a relation is said to be an equivalence relation under certain condition. So the first thing, sorry, maybe just scroll a bit too fast. So relation on a set is said to be an equivalence relation if some condition holds. So as you see, to learn the notion of equivalence relation, we need to first learn the notion of a relation. Okay, so let's try to do that. I'm sorry. So a relation on a set S is a subset R of S cross S, and if AB are elements of S such that AB lies inside R, then one says that A is related to B by this relation R. So let's read this definition once again. There is just no other choice. So relation on a set S is a subset of S cross S. So it's a subset R of S cross S, and if we pick two elements A and B from this set such that this pair A comma B lies inside R, then one says that A is related to B by the relation R. Okay. So the first thing that one may note is that R is a subset of S cross S. Okay. So it may happen that A comma B lies inside R for some specific choices of A and B, but it may certainly happen that B comma A does not lie inside R. Okay. So if B comma A does not lie inside R, we will not be in a position to say that B is related to A. Okay, so it may very well happen that A is related to B, but B is not related to A. Okay. Anyway, so I hope you already have an idea what's going on, but let me try to provide certain examples to illustrate this notion. Okay. Yeah. Mm. Yes. Yeah. So you have to first start with a set S. Okay. Let's start with a very easy set. Let's take S equal to 1, 2, 3. Okay. I mean, if you don't like this set, you can also consider, consider this set ABC. Okay, so you can ask what is ABC. So yeah, ABC could be. Uh, so what are this? So what are this ABC? So ABC, they could be. Oops, they could be three persons. Okay. Oh. mm, mm, yeah, they could be three persons. Uh, and okay, I'm just trying to think of few nice examples that can illustrate this notion of relation and some of the some of the further specific relations that we will be learning in a moment. Anyway, so let's try to just deal with the very first one, that is s equal to 1 to 3. Okay. uh, yeah, so what do you know about all this? So 1 2 3, for example, we I mean, what can we say? So 1 and 2, I mean, so we know that 1 is less than 2, right? So there are a few things that you know about 1 2 3, that 1 is less than 2, 1 is less than 3, 2 is less than 3. So I mean, this is a relation, right? I mean, okay, so relation in the knife sense, okay? So right now, for a while, I'll be using the terminology relation in a knife sense, okay? And then I'll try to indicate that our very naive and the usual understanding of relation uh, is captured very well by the definition of relation that we have above. Okay, so I'll speak about the notion of relation in a somewhat naive manner, and the next task would be to convince ourselves that uh, the above definition uh, summarizes, or rather kind of the above definition makes the notion of the notion of relation that is defined in this definition 59 is modeled on our usual understanding of the notion of relation. Okay, and then onwards we will not have any discussion about our naive understanding, because to do math we need to define some terms, but at the same time we need to probably kind of make sure that, which is also not required, but it's a good idea to kind of make sure that such terminologies are quite appropriate. Okay, anyway, so we have already come up with, I mean, you already know that such relations, for example, this is a relation, right? I mean, between 1 and 2, that 1 is smaller and 2 is bigger, and this is also a relation between 1 and 3, that 1 is smaller, 3 is bigger, and so on. Okay. So what are the relations that we get from here? uh, I mean, mm, so let's try to record all these relations in a nice manner. Okay. Yeah, I mean, you may also say that, okay, there are other ways of relation that one can think of, right? uh, an immediate one would be to look at the relation that I mean, mm, that, for example, you know the divisibility condition: 1 divides 2, 1 divides 3, and of course, I mean, we can't write 2 divides 3, right? So this is also kind of a relation. There's also few relations between these integers. Okay. mm, so this is a divisibility relation, divisibility relation. Okay, great. Then yeah, so you're trying to kind of record this information in a somewhat nice manner. Anyway, so it's important to kind of know what we are dealing with. We are dealing with this less than and less than relation. Here you're dealing with this divisible relation. But if you remove all that, okay, just remove this, I mean, for a while, okay, then what do you get? uh, so here what we have is 1 comma 2, that 1 is related to 2, and we have that 1 is related to 3. We also have that 2 is related to 3, right? We also have that 2 is related to 3, and here we have that 1 is related to 2 and 1 is related to 3, and that's all. Okay. Sometime uh, yeah, so one may one may so one may think of this one may think of this as a how to say, kind of a summary of this information, okay? And even here also one may think of, oops, here one may think of this as a summary of this information. So that is what is being done. Mm, to think of this, so what is this? I mean, this is a bunch of few tuples, okay? And usually when we deal with several things, we just form a set using that, using them. I mean, so what we do is just consider this set. So note that, now which one to use? Maybe red. So this is a subset of this is a subset of S cross S, right? And what is this? This is also a subset of S cross S. So what you see is that so this relation, this information is summarized by this bunch of tuples, or in other words, this relation, this information is summarized by this set consisting of certain tuples, and this is a subset of S cross S. Okay, and even here this information is summarized or is captured, okay, rather this information is captured by this subset of S cross S, right? So that's what is being highlighted here, or being used as a defining criterion. So a relation on a set S, so this is a relation on this set S, so this is a subset of S cross S, okay? So this relation or this information is captured by this set of S cross S, okay? So please go through this once again, please watch it what I have been saying once again, or maybe few times, just to make sure that you understand this statement, and you are able to appreciate, and you see that this should have been a way, or this could have been a way, or at least this I mean, this makes perfect sense if we have these two examples in mind, okay? And as I said, uh, as you see, I mean, as I said, that it may happen that A comma B lies inside R. In other words, A is related to B, but it can happen that B is not related to A. Okay. So an example of such a situation is that. Oh, again, need to load it. Hmm. Uh, yeah, so as you see that we know that 1 divides 2, we know that 1 divides 2, but 2 does not divide 1, okay? So 1 comma 2 lies inside, so 1 comma 2 1 comma 2 lies inside this subset of S cross S, but 2 comma 1 does not lie, okay? So 1 is related to 2, but 2 is not related to 1, okay? Mm, let's see, let me just write few sentences. So here, oops, here 1 is related to 2, 1 is related to 3, and that's all, okay? These are all the relations that we have here. So 2, so 1 is so 2 is not related to 1, 2 is not related to 3, okay? Okay, how many we will get? Ooh, okay, anyway, so uh, just now I thought that something incorrect is going on. You may also say that 1 also divides 1, so why didn't you include 1 comma 1 here? Yeah, maybe I should have included, I'm sorry. For some reason I had this, oh sorry, for some reason I had, I mean, this proper divisibilities in mind. Anyway, so let me also include that, because in mathematics divisibility, I mean, when one talks about divisibility, one doesn't have this notion of proper divisibility in mind, okay? So let me try to rectify this. Hmm. Just give me a moment. I mean, I think you have already understood what I was trying to highlight. Yeah, so 1 divides 1, 1 divides 2, and then 1 divides 3, and then what else? So 2 divides 2, 2 does not divide 3, 3 divides 3. So along with all this that I have here, I should have included, or maybe just let me rewrite it. Yeah, so this should have been 1 1 1 2 1 3, 2 2, 2 3, and that's all. Okay, and so this is a subset of s cross s, and writing all that would take a while, so let me uh, delete, and then 1 is related to 1 is also related to, I don't know what to do. Oops. Just give sorry, just give me a moment. I thought of just describing this while, describing it. I didn't. Oh, sorry. I should have just circled it. Yeah, I thought of describing this. Yeah, describe. Oh, okay. There was a warning. Yeah. So yeah. So one is related to one, and then 2 is related to 3, and then 3 is related to 3, etc. Anyway, so by now I think you have understood what I was trying to say. And here, as you see that I have taken 3 people, ABC, 3 persons ABC, and formed a set using that. And uh, so, for example, so let me just write it once again. So we have this set ABC, where ABC are 3 persons, and we may try to introduce a relation between them. So for instance, if we say that, so as a definition, we say that A is related to B if if uh, if A is oh, if A is shorter than B. Okay. Yeah, so now you can ask me what do you mean by shorter. So there, the height of A is less than or equal to the height of B, not less than. So yeah, this is the relation, right? And and for instance, you can also define a relation. You can also define a relation between these 3 persons by their nationality. Okay, so the 3 persons from this world. So you say that 2 persons. Okay. So A and B appear to be quite specific. uh, Sorry. Oops. So I should erase this. You can say a person P1 is related to a person P2 if P1 is shorter than P2. Okay. Uh, yeah, and one can also define another relation on the set by the nationality of the people. So P1 is related to P2 if P1 and P2 have the same nationality. Okay. Or for instance, if one can one can introduce a lot more relations. For instance, if they are P1 is related to P2 if they are siblings and so on. Okay. For example, one can another relation could be P1 is related to P2 if they are neighbors. Okay, something like that. Okay, anyways, we have had enough about all these relations. So let's just read the definition once again, and let's move on. So relation has to be thought of as a subset of S cross S. Okay, and for example, if 1 comma 2 or A comma B lies inside the given relation, then one says that A is related to B. Okay, and when one says that A is related to B, for instance, in this case, one would write A is less than B, and in this case, one would write A divides B, like a vertical line B, and so on. So so yeah, one will write something like this or something like this, etc. Okay, one can also write something like A tilde B. One can also write A equivalent to B, or A is congruent to B. Yeah, so for example, the notion of congruence, this is something that you have seen in that all of us have seen in our high school days. So now I have for yeah, there is notion of similarity and there is notion of congruence. I have forgotten which one is which one. uh, uh, Anyway, so for example, this triangle, okay, there's a two gener. So this triangle is one can relate this to triangles. uh, oh, Yeah, so one can relate this to triangles. I mean, this side, the length of this side is equal to the length of this. So the length of this side, I mean, length of these three sides is same as the length of these three sides. I mean, when you have enough faith in my drawing, you can assume that the length of these three sides is same as the length of these three sides, respectively. So then this is triangles. I think they are said to be congruent. Okay, I don't remember. I mean, one can also scale. I mean, one can also scale them, and then probably one gets this notion of congruence or similarity. One of these two. Anyway, so this notion of relation is something that we have. I mean, we are actually familiar with. So we'll be using this symbols, this tilde or this. I mean, this one or this one or this, etc. Or maybe this divisibility. Okay, this vertical line that A divides B. So we'll use this notation. We'll use these notations to denote a relation. Okay. So as you stated that a relation has to be a subset R of S cross S. Sometimes we may say that this less than is a subset of. I mean, less than itself is a relation. Okay. So R stands for. So when you say that we have to have a subset R of S cross S, instead of that we will say that suppose we have a relation less than contained inside S cross S. Okay. So don't be surprised. So we'll somehow at sometimes we'll replace R by the symbol less than, or maybe this one of this. Okay, great. And then says that if tilde is a relation on a set A, and if A B are two elements of S, so that A is related to B. Okay, and it means that A comma B lies inside the relation R, and as I stated, R is denoted by tilde now. So A comma B belongs to A comma B belongs to tilde. then then one often kind of shortens this in this form, that A is related, I mean A tilde B. Okay. So for example, in the very first instance, we would say that we said that one is less than two, right? One could also say that 1 comma 2 belongs to this relation less than. Okay, so this is also one way of saying that 1 is less than 2. Yeah, so please go through all this once again. I think after reading it a couple of times, you'll become familiar with what I have been trying to highlight over and over again. So relation R on a set S, so there is a subset of there is a given subset R of S cross S is said to be reflexive if A comma A lies inside R for any A inside S. Okay, and this notion of symmetry, as I stated, A might be related to B. I mean, it may happen that A is related to B, but B is not related to A. Okay, so symmetric relations are those where this kind of situations doesn't occur. Okay, in other words, whenever A is related to B, you immediately have that B is related to A. Okay, so relation R on a set S is said to be symmetric. Is said to be symmetric if A B are elements of S such that A is related to B, then B is also related to A. Okay. And there is another notion, this notion of transitivity. For example, you know that with this less than, so less than has certain transitivity property. By that I mean, if A is less than B and B is less than C, this information implies that A is less than C, right? This information implies that this information implies that A is less than C. So if some such situation holds for a given relation, then we call, this holds, this implication holds for any ABC. Okay, if ABC are real numbers or integers satisfying these two inequalities, then this third inequality has to hold. So if for a relation some such thing holds, then we call it transitive. Let me explain what do I mean by some such thing. I mean that if ABC are elements of, if R is a relation on S and ABC are elements of S such that AB and BC both lie in R, in other words, A is related to B and B is related to C, then we have that A is related to C, or in other words, AC lies inside R. In such a situation, we say that this relation is transitive. Okay, so note that whenever this has to hold for all choices of ABC. For all choices of ABC satisfying this condition has to hold. Okay. So now time to have certain concrete examples, maybe, or certain more examples. There are certain examples that you already know. For example, this less than, or for example greater than, or this divisibility, etc. Right? uh, give me a moment. I just wanted to provide, how do we introduce another page? Yeah, I just wanted to provide another example. That example might appear somewhat, I don't know, out of the context maybe, or at least quite stupid. Uh, mm, yeah. Mm, how to write all this? Yeah, so it has to be an exercise. Consider the relation tilde on mm, on maybe the set of all non-zero numbers. Okay, consider the relation tilde on z minus 0 defined by, so you say a is related to b if the LCM if LCM of a and b is a prime number. Okay, then this is the exercise you just considered. So the task is to determine if tilde is, as you can see, I mean, probably you can imagine whether that is reflexive, symmetric, transitive. Okay, so to determine how many of these three properties, I mean, how many of these three properties does this relation tilde have? Okay, this is a well-defined relation. Okay, check that this is well-defined, or convince yourself that this is well-defined. Okay, great. So yeah, so here is another relation, quite important. Oh no, so this is not that important because we will not be dealing with this relation much. I mean, this doesn't have much group theoretic significance. Okay, I do not know any group theoretic. I do not know much group theoretic significance of this relation. So we say that a is, I mean, so on this set of integers, we say that a is related to b if a is less than b. Okay, so this still, so this, I'm sorry. So this relation consists of the tuples a comma b, where a b lie inside z, and they satisfy this inequality a less than b. And again, as you can imagine, your task is to determine whether there is transitive, whether there is reflexive or transitive or symmetric, etc. Okay, the transitivity is clear, as I said, because you know it from high school days that if a is less than b and b is less than c, then a less than c has to hold. Okay, so transitivity is clear. So it's your task to determine the whether this satisfies the other properties. It's reflexivity. I mean, this reflexive and symmetry, whether these two properties hold for this relation tilde. Okay, and now we can define another relation on the set of all positive integers. We say that a is, I don't know how to read, maybe less than or equal to b if a divides b. Okay, so this is reflexive and transitive. Okay, yeah, so now you can define another relation on the set of all positive integers. So we say that a is less than b or less than or equal to b if a square divides b. Okay, one can check that this is transitive, and one can determine, one can show that this is neither reflexive nor symmetric, etc. Okay, so this example 66 is going to be of very crucial importance in the course. So you say that when we define a relation on z as follows. You say that a and b are related to z if a minus b is an even number. Okay, since a minus a is even for any a inside z, it is clear that this relation is reflexive. Moreover, if you know that a minus b is even for a b inside z, then certainly b minus a is also even. So what we get is that this relation is symmetric. Okay, once again, note that if moreover, note that if a minus b and b minus c are even, then a minus c, being the sum of two even numbers, that is also even. Okay, so this shows that this relation on z is transitive. So this relation, what you have just seen, is reflexive, symmetric, and transitive. Okay, so such a relation is called an equivalence relation. That is a relation on a set S, having all these three properties, that it is reflexive, it is symmetric, and it is transitive. Okay, In that case, we say that it is an equivalence relation. Okay. So we'll try to see that we'll try to see that a more general situation holds. In a more general, one can get a, this is a special case of something more general. So if you take a positive integer n, and then one can define a congruence modulo n relation on Z as follows. So you take two integers a and b, one says that a is related to b, or in this case, a is congruent to b modulo n, and one writes a congruent symbol b mod n if a minus b is divisible by n. As you can see, here we have been focusing on the situation that a minus b is an even number. In other words, we had n equal to 2, we had n equal to 2 in this example, right? So now the task is to show that this defines an equivalence relation on Z. Okay. Here is another way to get an equivalence relation on a given set. So if you have a set S, and if you have a map phi from S to T, then if you look at its fibers, in other words, you say that two elements A and B, they're related to each other. Given two elements A and B, you say that A is related to B if they have got equal images. Okay. And thanks to such a definition, it is clear that if A is related to B, that is when phi equal to phi B, at that time B has to be related to A, because phi equal to phi B is same as saying that phi B equal to phi A. Thus A is related to B is same as saying B is related to A. Okay. In other words, A related to B and B related to A, they are equivalent. Okay. So it is clear that this is reflexive. The symmetry and the transitivity is easy to see. And this has, it's easy to see, and you should you should go through this easy step. You should go through this easy exercise. Okay. For example, this is symmetric because, Okay. What I just said is that is symmetric. So there is reflexive because if you give me A from S and element A from S, I know that phi A is equal to phi A because phi is a function. So A is related to A. So this is reflexive, and this is symmetric because phi equal to phi B holds if and only phi B equal to phi A. In other words, A related to B if and only B is related to A. That's why this is symmetric, and the transitivity can also be checked without much effort, or with a very minimal effort. So one can, in other words, this tilde is an equivalence relation because it has all three properties. It's your task to determine, to verify that, or that all these three properties are satisfied by this equivalence relation tilde that you have just defined. Okay. So one says that this is the relation induced by this map phi. Okay. Okay, great. Now here is an exercise. So so you have just defined here a congruence relation, a equivalence relation. It's your task to prove. So let's assume that you have proved it. So we have defined an equivalence relation on Z. Okay. So now it's your task to see whether this equivalence relation can also be obtained from example 67. In other words, can one define a map phi from S to T, okay, or in this case, can one define a map phi from Z to T, okay, for some set T, such that the relation on Z induced by phi is a congruence modulo n relation on Z, okay. So the relation on Z induced by phi is the one that we are referring to as per the notations of example 67. So this becomes a congruence relation, congruence modulo n relation on Z, that is this one in exercise 69. Okay, so please work on this problem, and here are certain further examples / exercises for you. So on the set of non-zero complex numbers C cross, one can define a relation as follows. We say that A is related to B if A, B have the same absolute value. It's your task to see whether or not this is an equivalence relation. I've already stated that you have this already states to note that this is an equivalence relation, so you know what's the answer. So please try to show that this is an equivalence relation. Okay. The next example says that so something probably went wrong, because this example 71 and 72, they look the same, right? Okay, you can walk twice, okay, if you wish. Okay, example 73. It says that if you look at, if you consider this relation on GL to C, okay, so what is GL to C? Just to remind you, so GL to C denotes the set of all 2 by 2 matrices with coefficients in, this E is missing. So the coefficients. Uh, yeah, it's the set of all 2 by 2 matrices with coefficients in C. That is, the entries of the matrices are from the complex numbers, okay, and they should have non-zero determinant, okay. There has to be a full stop here anyway. So this is GL to C, and one can consider this following relation on GL to C defined as follows. Given two elements A and B inside GL to C, we write A is related to B, or we say A is related to B if A and B have the same determinant. So note that this is an equivalence relation. So please try to work on all these problems, okay? Yeah, so let me conclude today's lecture here, and the next lecture we will continue with this equivalence relation. Next couple of lectures we'll be working on this equivalence relation and certain specific examples of equivalence relations. Okay, let me conclude.